All right, so we're going to talk about the anisotropic effect. But before we get to the detail, you should be able to explain, right, or understand how a proton is shielded or deshielded. Okay, so not much memorizing here. The hydrocarbon, nothing deshielded the proton, so show up upfield, the most shielded protons. When this proton attached to the electronegative atom, so become more deshielded, so shift to the left side downfield, 3 to 4. All right, and we were talking about the proton on an sp2 carbon on an alkene about 5 to 6, and aromatic compound about 7 to 8. Okay, this one you might think, hey, there's no electronegative atom, so why these two protons are that deshielded? Well, this is because of anisotropic effect. All right. Before I talk about anisotropic effect, so you can read the detail behind it in a textbook. But I just want to just touch just a little what you just need to know. So this won't become memorization. All right. Now here is the anisotropic effect. Let's take a look. The proton right here, right? So shielded, deshielded depends on how much electron density it has. All right. All the proton sample we take let's say when we take proton NMR, we put into a machine, and in machine produce external magnetic field go up to that direction. I use B with a hat, doesn't use it in physics. Okay, that's a magnetic field and go pointing up. All right. So this proton, of course, gonna feel that the strength of magnetic field, but protons feel it differently. Depends on how much electron density each one of them have, or shielded, deshielded. The shielded proton won't feel that much. The deshielded proton will feel the strength of external magnetic field. All right, and here's what happened. All right, the benzene also got some electrons in there. Right, show some electrical current. In physics, electrical current produces a magnetic field, its own magnetic field, and the direction of magnetic field goes with the right hand rule, something like that. You could go with the take a look in physics in there. But anyway, so the pi electrons on a benzene ring produce its own magnetic field in that direction. Now let's take a look. Before we add the magnetic field from the pi electrons, this proton already feel the magnetic field outside, right? From an instrument. Add on to it. Look at the outside. The magnetic field from the pi electrons going up the same direction as external magnetic field. So this proton will feel the strength of magnetic field even more, right? So this proton will become more deshielded. Okay, so we call right here deshielding zone, deshielding zone. That's why the proton outside the benzene ring really deshielded, because the feels external magnetic field, and also feel the strength of the magnetic field from the pi electron. They add up to each other, make this proton highly deshielded, and the chemical shift go up to 7 ppm. Okay, now some of you think, hey, are you making this up? But no. When people propose this, yeah, people think the same thing. Are you making this up? Can you prove it that this proton actually get really deshielded? There's a deshielding zone outside here. Well, here, let me tell you this. Look at the inside the benzene ring. Okay, I want you to look at the direction of the magnetic field from the pi electrons, pointing down, opposite direction from the external magnetic field. Which means that the strength of magnetic field inside the ring will cancel some each other out, right? So we have a shielding zone right here. Let's say that if we can put a proton inside the benzene ring, they're gonna be shielded. Okay, because we have deshielding zone outside. The two magnetic field add up to each other. The inside they cancel each other. Right, so this is what happens. So some people make this molecule, put a proton inside the benzene ring. Guess what happened inside right here? This proton has a chemical shift of -1 ppm, highly shielded. And that, look at this. We have aniline compound. Right, the outside aniline, the proton have chemical shift about 8.9 ppm. The inside one though, -1.8, highly deshielded, even deshielded than more deshielded than a TMS, the reference compound. Okay, all right. The alkene also deshielded about 5 to 6, and here's the same reason. Put into external magnetic field, this two proton feel that magnetic field, but the electron inside the pi bond in here also produce its own magnetic field, and it add up to the external magnetic field. So these two protons actually feel even more, become d-shielded. All right, how much d-shielded? 5 to 6. If we can put the proton inside, in the shielding zone, this proton would have less, would be very shielded. Okay, that's why. So the chemical shift of proton on alkene and proton on benzene, 5 to 6 and 7 to 8, because of anisotropic effect. Aldehyde, that proton right there on sp2 carbon, 9 to 10, goes up to 9 to 10, and carboxylic acid goes even more, 11 to 12. Here's the reason why. Okay, so this is an alkene, and aldehyde is, I'm going to replace that carbon with the oxygen. That's an aldehyde. You know, that's an aldehyde. That proton right here, highly d-shielded. One, because of it's in the d-shielding zone, and also that oxygen is highly electronegative. Okay, so from 5 to 6 on alkene, add that oxygen, go up to 9 ppm, really high. Okay, sometimes 9 to 10, about that, but about 9. All right, carboxylic acid as well. So we have proton from anisotropic effect, oxygen de-shielding it, right, and oxygen de-shielding it right here, and plus the hydrogen bond from a different acid, they can form hydrogen bond, also de-shielded that proton even more. So as a result, the chemical shape of that proton is 11 to 12, super high. Okay, that's why we got it right there, right here. So basically, all right, so what could de-shield a proton? So we have electronegativity. We have anisotropic effect, all right? Aldehyde is a multiple effect now. So we have anisotropic effect plus inductive effect. On carboxylic acid, we got anisotropic effect, inductive effect, and hydrogen bond. Okay, that's why you get this. You see the trend there. On alkyne, right? So alkyne a little bit weird, but I put it right here. So we put in external magnetic field. The magnetic field from the 4 pi electrons, the pi bonds, goes into that direction. Take a look. This proton right here is actually in a shielding zone. Okay, so the chemical shift is not that high. It's only 2.5 ppm. And I put alkyne down here with the alpha proton. It's not an alpha proton, but the chemical shift is close. So I group them together. All right, we almost there. So last one, we're going to talk about hydrogen bonding on the next video.